This should be the first video you watch for pulsed echo instrumentation. It'll cover the basics of PEI and the pulsar and beamformer. So we've already dedicated a lot of time to learning about the transducer and that it creates pulse waves to create anatomical pictures, but now we need to learn how the machine creates those pulse waves and displays them. Because we do use pulse waves, our ultrasound machines are called pulsed echo instruments. These types of machines have two major roles. The first is to prep and transmit the sound beam, and the second is to receive the sound beam back and display it. There are 6 major pieces to the pulsed echo instrument. They are the transducer, the pulsar and beamformer, which both create the transmitter, the receiver, the display, storage, and master synchronizer. This slide kind of shows us a roadmap for instruments that do not use pulse waves, and they're set up like this. These are typically for single crystal transducer systems. So we start with the pulsar. From the pulsar, heads into our electrical signal, heads into our transducer. Our transducer then generates the sound beam. It goes into the body and then comes back to the transducer. The transducer will switch that sound energy back into electrical energy, which moves on to the receiver. After it is in the receiver, it gets transferred into memory, and then lastly, it is displayed. However, when we are using pulse waves, we need to add in another step called the beamformer. Remember that an array transducer uses the beamformer, but follows mostly the same process. So again, we start in the pulsar. This is going to send voltage to the beamformer. At the same time, the switch will inform the receiver and the memory that a voltage has been sent out and also protect them during this process. So that electrical volt gets sent over to the beamformer, and the beamformer is going to determine what type of delays and phasing is going to occur with that electrical information. So all those little electrical bits then travel down the channels to the transducer. The transducer will generate the sound pulse. Sound pulse goes into the body, returns. The returning sound pulse gets switched back into electricity, which will go back through the beamformer, and that will decide how the electricity gets sent to the receiver. The receiver then is going to process those data bits that are coming back by going through amplification, compensation, compression, demodulation, and rejection. After all those 5 processes are handled, that information is sent to the memory, where it is manipulated and then sent onto the display, where we can actually see it on our TV screen. We're going to cover all those pieces in depth over the next couple of chapters, so we're going to start with the pulsar. The pulsar is the controller for the sound pulses. This is the part of the machine that produces that electrical voltage that drives the transducer. The pulsar operates at frequency of the probe, so sending electrical signals to the transducer at the same rate the transducer will produce sound pulses. So if we have a 2 megahertz transducer, that voltage is 2 megahertz, the sound pulse is 2 megahertz. They match up. Because one voltage signal equals one sound pulse, the PRP and PRF of the pulsar are equal to that of the transducer. The amplitude of the wave is also determined by the pulsar. The pulsar only operates during transmission of the sound beam. The pulsar is responsible for the transducer output. The output can be adjusted by the change in the voltage of the electrical pulses created. If the pulsar sends out a low voltage electrical wave, the sound beam is going to be weak and the image will appear dark. The opposite is true as well. If we have a high voltage coming out of our pulsar, we get a stronger sound beam, therefore a brighter image. Some synonyms for the energy created by the pulsar are output gain, acoustic power, pulsar power, energy output, transmitter output, power, and gain. Make sure you don't confuse this gain with the 2D gain, as they are different and play a role in bioeffects for patients. The most common term for this is most likely power. On the Philips machines in our labs currently, there is a button labeled power that will change the voltage coming out of the pulsar. Because the pulsar decides how much energy is put into the body, we need to monitor that output of the pulse by watching the TI, or thermal index, and the MI, the mechanical index. These two parameters tell us the likelihood of the tissue heating up and cavitation occurring. If the energy output increases too much, causing too much heat or cavitation, bioeffects or cell damage may occur. We can adjust the output energy, but when we do so, the whole picture is affected. As we saw in the last slide, high voltages mean strong beams, which mean bright images. So it's important for sonographers to keep the voltage to the minimum needed for optimal pictures. The next time that you're on a machine, try to find where that MI and TI are labeled. I have a picture of a right kidney here, and up in the corner is the TI and the MI. We're going to compare those to a first trimester ultrasound where MI and TI are here, because we want to protect the fetus and make sure that it is not being subjected to too much power coming from the ultrasound machine. You can see the MI and the TI are much lower than what they were for the kidney. Go through different settings and see what the MI and TI change. These are also responsible for finding out how these change for your physics paper. Another thing that happens when we adjust the output of the pulsar is the signal to noise ratio. When we increase the power output of the pulsar, we increase or improve our signal to noise ratio. The signal to noise ratio is a comparison of meaningful reflectors to just kind of background noise. So again, it's important to set the output power appropriately for the best picture possible. As I mentioned before, you do not want to confuse output power gain with receiver gain, which is that knob on our machine that says gain makes our pictures brighter or darker. So as a rule, we should always reduce our output power first and then adjust the 2D gain. Again, try to get on a Philips machine and check out the knob labeled power. See what it does when you increase it and decrease it, paying attention to what the MI and TI do. If the machine doesn't have a knob for power, try different settings and see what the MI and TI do in that case. As sonographers, though, it is important to follow ALARA. You need to know what ALARA means. It stands for as low as reasonably achievable. So again, we are going to be setting our output power as low as we can to get accurate diagnostic images. So it's important that if our picture is very bright, that we are decreasing our output power first, and that if our picture is way too dark, we want to try increasing the receiver gain first before changing to the output power. The beamformer combined with the pulsar is considered to be the transmitter, and this is associated with array transducers. So again, beamformers are only in array transducer systems. The beamformer is responsible for receiving the pulsar's electrical waves and distributing it to the transducer. The beamformer is responsible for creating those complex steering and focusing patterns that move down the channels to the transducer. It also is responsible for apodization to reduce grating lobe artifact. After the sound returns from the body through the transducer, it again goes through the beamformer, where those electrical signals are processed for dynamic receive focusing. The other responsibility of the beamformer is to control the dynamic aperture. Dynamic aperture is the machine deciding which PCT crystals should be activated during the transmission and reception of sound beams. In our current systems, we use digital beamformers. Modern technology has allowed us to use microprocessor technology to create beamformers that are much more stable versus mechanical beamformers. They are also easier to update as it's just a software change versus completely taking out the beamformer and replacing it. And then they're also very versatile. They can work with multiple probes. As you can tell with our current machines, we're plugging different probes in all the time and the machine has no problem recognizing and operating them. Two other components that include the transmitter are the switch and the channel. Channels we've already talked about, and you know that they consist of one PCT crystal and one wire that connects back to the beamformer electronics. So that's the part of the channel that is in the transmitter. The other part is the TR, or transmit receive, switch. The TR switch directs voltage to the transducer in transmit mode and then protects the receiver and memory from the strong electrical pulses being sent out. As the sound comes back, the TR switch then directs the voltages to the receiver for processing. All right, it's again time to test yourself. Number 1, what component is not required for single crystal transducer systems? Is it A, pulsar, B, receiver, C, beamformer, or D, display? Number 2, a sonographer is scanning a fetus and thinks the picture is too bright. To reduce bioeffects, what should the sonographer do first? A, increase power output, B, switch probes, C, increase receiver gain, or D, decrease TGCs. Number 3, the beamformer does all of the following except A, steering and focusing of sound beam, B, produces voltages, C, dynamic receive focusing, or D, apodization.